Good morning everyone. So, we are looking into the gas separation by membrane based processes. In case of gas separation of membranes, the first characteristic or the first difference of these membranes compared to the other membranes where we handle the liquid materials is that the pore size is very small in these membranes. So, these are very dense membranes. So, the first characteristic in gas separation by membranes is that the membrane that you are going to use, it is a very dense membrane. Okay. So, the gas species, gaseous species only will diffuse through the membrane based through the membranes. Now, typically the feed side pressure is very high, feed side high pressure, that means you are injecting a gas at a high pressure to the feed side and the permeate side is of low pressure. In sometimes the permeate side is kept under vacuum. So, there will be a tremendous pressure gradient or delta P will be occurring at the across the membrane, and the species that will be permeable through the membrane, it will be gets transported from the feed side to the permeate side. Now, the another characteristic is that the gaseous material, gaseous species will be having definitely a high diffusivity compared to the liquid the solute diffusivity in a liquid stream. So, gaseous species is having high diffusivity, and because of high diffusivity they are well mixed in the stream. That means, because of the diffusivity there is less probability that there will be formation of boundary layer or sort of thing in the feed side or in the permeate side. So, therefore, because of high diffusivity of the species, the feed is assumed to be well mixed. Okay, feed is assumed to be well mixed. That means, there is no concentration gradient of solute in feed side. So, it is that means the concentration is uniform, that means concentration, solute concentration or species concentration is uniform. So, that is an assumption, and it is a valid assumption simply because of the fact that the gas diffusivity of the gaseous species are extremely high. So, therefore, you can neglect the gas film resistance. Gas film resistance can be neglected. Okay. So, these are silent some of the salient features of the gas permeation through the or gas separation by the membrane. Now, depending on the flow configuration, the system can be categorized into several categories. Characteristic we have various kinds of flow configurations. Okay. What are these? Number one is that simple cross flow. In simple cross flow configuration, the gas will be fed in the feed side, and the permeate will be coming normal to the direction of the membrane in the permeate side. So, it is called a cross flow. That means, direction of the feed flow and the permeation direction of the species will be at 90 degrees. So, that is a cross flow configuration, simple cross flow configuration. If the feed side and the permeate side are both well mixed, that means they are well stirred. That means whatever the concentration gradient, if there is, if at all it exists, it will be well mixed. So, this is known as the complete mixing flow, complete mixing model or configuration, or completely mixed flow. It will be like CSTR, continuous start type reactor, that means it is well stirred and the concentration is uniform throughout. If the flow direction of the feed and the permeate are in the same direction, then it is a co-current flow. Flow direction of feed and permeate is same, then it is a co-current flow. And if the flow direction of the feed and permeate are in the opposite direction, then it is called a counter current flow. And we know that counter current configuration is much more efficient compared to the co-current configuration, that we have already seen in the heat transfer cases for the heat exchangers, we have already seen in the mass transfer cases in dialysis. Okay. Flow direction of feed and permeate is opposite, then it is known as the counter current flow. So, if we have a system something like this, suppose you place the membrane in between, dividing the whole chamber into two parts. This is the feed going in and you are collecting the permeate. Feed is going into the system, then the reject stream is coming out of it, and the permeate you are going to get almost at 90 degree to the direction of the feed flow. This is a simple cross flow system. On the other hand, if you have almost the same thing, but both the chambers are well stirred, then it is a completely mixed system. There is a second configuration we have discussed. So, this is the feed, this is the reject, and we are going to get permeate out of it, and both the chambers are well stirred. Okay. So, this configuration is known as completely mixed configuration. Completely mixed system. Okay. On the other hand, next two will be, if you do not have the stirrer or something like that, if you use a carrier gas or a neutral or non-reactive gas, so that the permeate will be taken out in a flowing stream, then it is called a co-current or counter current, depending on the direction of the flow of the permeate and direction of the flow of the feed. For example, if we have a system something like this, where both the chambers are separated by a semi permeable barrier or the membrane, and you will be having a feed here, feed is going into the system and the reject stream is coming out of it, and similarly the permeate is flowing by a carrier gas, the permeate is flowing in the same direction. Okay. This is a co-current configuration. On the other hand, if we have the opposite, the direction of the flow are just opposite, you will be having the counter current configuration. is the permeate. So, it is a counter current configuration. Now, there are two different approaches. We already know what are these approaches when you would like to analyze these two systems. For example, if you would like to talk about the completely mixed system, it exactly works like a CSTR, that we have already done the modeling of completely starting reactor in our reactor analysis course, as well as plug flow reactor, right. So, we have two types of reactors, that is the CSTR and the plug flow reactor. In this case, the analysis will be like a CSTR analysis. For example, the concentration is uniform, it is assumed to be uniform throughout the whole length or the region of the permeate and the feed. On the other hand, if you have a co-current or counter current configuration, then it is basically like a plug flow type of analysis you are going to do. Okay. So, if you remember the fundamentals of plug flow reactor, at every location, so concentration varies at every point of length. So, whenever we are talking about a co-current or counter current configuration, the analysis that we are going to adopt is the plug flow reactor analysis. On the other hand, whenever we are talking about the completely mixed reactor, we will be taking recourse to the CSTR type of analysis. Okay. Now, what we are going to do next is that we are going to calculate the looking into the working principles and the calculations those are involved in the configurations that we have discussed. The first configurations we are talking about is the completely mixed configuration. It is like a CSTR type of analysis. Okay. Now, let us jot down the assumptions involved. Assumptions involved in this analysis are: number 1 is that isothermal condition. There is no change in temperature during the operation. Secondly, negligible pressure drop in feed and permeate side. The pressure drop in feed and in permeate are negligible. Okay. And the permeability of each component is constant. That means, you will be having a stream containing two components A and B. You are going to separate A and B by the membrane. So, it is basically in the gas stream. So, the permeability of both the components. So, permeability of both the components will be present. That means, both the components will be permeable. One will be less permeable, another will be highly permeable. So, the component that will be highly permeable, the permeate stream will be rich in that particular component. So, that is the idea. So, now we are assuming that permeability of both the components will be constant, because we are maintaining the temperature constant. Since the diffusivity is a strong function of temperature, since we are maintaining the temperature constant, the permeability is also supposed to be constant in this. Okay. So, let us do the analysis for the completely mixed configuration. This is the high pressure side, that means feed side, high pressure side. This is the low pressure side or the permeate side. So, you will be having the feed that is going into the system with a flow rate QF, and the mole fraction of the component that we are talking about to be separated is XF, and there is it is completely mixed up, and this is also completely mixed up, and we have a flow rate that is going out is nothing but 1 minus theta times q f. What is theta? Theta is the volume fraction of the fraction of the feed that is going into the permeate. So, the permeate stream will be having q p is nothing but theta times q f. What is theta? Theta is basically the fraction of the feed that is going into the permeate. So, 1 minus theta of q f will be coming to the q naught, and the pressure in the feed side is assumed to be constant. So, it is pH, and x naught is the mole fraction of component in feed, and this is PL y P. PL is the pressure in the permeate side, the low pressure side, and y P is the mole fraction of the component in the permeate. So, y indicates the permeate stream, x indicates the feed stream, and the mole fraction of the component that is in the feed, that is going out. Okay, mole fraction of component in feed going out of the system, and you just see, observe that the quality of the permeate that is going out of the system is assumed to be same here. It is an assumption regarding to the CSTR analysis. That means, whatever the concentration that is going out of the system will be having the same concentration within the reactor, because it is a start tank reactor. Okay, it is completely mixed reactor. So, what is, let us write down all the notations clearly. QF is total feed flow rate, in meter cube per second. Q naught is the outlet reject flow rate, in meter cube per second. Q p is the outlet permeate flow rate, in meter cube per second, and theta is the fraction of feed in permeate. That is Q p divided by Q f. Okay. So, these are the notation that we are going to use, and so let us write down the overall material balance. So, if you write an overall material balance, you will be getting total flow rate that is going into the system will be total flow rate that is going out of the system, Q naught plus Q p. Okay. So, this is basically should be multiplied with the density of each stream, so that it becomes kg per unit time, but we are assuming that density of all the stream will be more or less constant. Okay. So, it will be Q f is equal to Q naught plus Q p. Now, rate of diffusion or permeation of species A in a binary mixture of A and B is given as Q A divided by A m is equal to Q p y p multiplied by divided by A m is equal to P a prime by L P h x naught minus P L y p. This is number 2 equation. Now, what is this? This Q A is the total flow rate of A in the permeate stream. Okay. Suppose we are talking about the separation of species A. Now, what is the total flow rate of A in the permeate stream? It will be total permeate flow rate, that is the Q p multiplied by the mole fraction of the species A, that is the Yp, okay, divided by membrane area. Okay, Am is nothing but the membrane area. So, it is flow rate of A per unit membrane area will be what? This will be nothing but the permeability. This is P A prime is the permeability coefficient divided by L. L is the thickness of the membrane multiplied by the driving force. Now, what is the driving force? Driving force will be the partial pressure of A in the feed site minus the partial pressure of A in the permeate site. What is the partial pressure of A in the feed site? The feed site, the mole fraction is x naught. X naught is the mole fraction that is going out of the system. Since it is a CSTR, it is a completely mixed system. So, what is the mole fraction in the that is going out of the system will be same as that is existing inside the system. So, pH is the total pressure in the feed site multiplied by the mole fraction of A in the feed site. So, that is the partial pressure of A in the feed site minus PL is the total pressure in the permeate site multiplied by the mole fraction of A in the permeate site. So, we write down the different notations. P A prime is nothing but permeability of A in the membrane. That is centimeter cube divided by per second centimeter square times centimeter of mercury. Okay, that is the pressure unit. Q A is the flow rate of A in the permeate, Okay. Am is the membrane area with a suitable unit, okay, that we will discuss later on whenever we will be solving some of the problems. Membrane area, okay. T is the thickness of the membrane, pH is feed site total pressure, that is centimeter of mercury. X naught is the mole fraction of A in the reject, X F is the mole fraction of A in feed, Y P is mole fraction of A in permeate, pH x naught, as I said, it is a partial pressure of A in the reject gas phase, and PL x naught, PL Y P is nothing but the partial pressure of A in permeate gas phase. Okay. Now, once you identify all the parameters, now let us write down the rate of permeation of species B through the membrane. That will be nothing but Q B divided by A M membrane area, and what is QB? QB will be nothing but QP multiplied by 1 minus YP. We are considering it is a binary mixture. Since the YP is the mole fraction of A, then 1 minus YP should be the mole fraction of B, divided by AM should be equal to PB prime divided by L pH 1 minus x naught minus PL 1 minus y naught y minus yp. So, this will be equal to, let me write it more clearly, P B prime divided by L pH 1 minus x naught minus PL 1 minus yp. So, this is nothing but the partial pressure of species B in the feed or the reject stream. Of component B in reject, and this is the partial pressure of B in permeate. Okay. This is the third equation we are talking about, and PB prime is permeability of species B through the same membrane. Okay. Now, what you can do? You can divide equation number 2 by equation number 3, and you will be getting as this QP will be cancelling out, AM will be cancelling out, and what you will be getting as YP dividing equation 2 by 3, you will be getting YP divided by 1 minus YP is equal to alpha star x naught minus PL over pH multiplied by YP divided by 1 minus x naught minus PL by pH 1 minus YP. This is equation number 4. What is alpha star? Alpha star is nothing but PA prime divided by PB prime. It is a non-dimensional constant, and this is a ratio of permeability of species A in the membrane and the permeability of species B in the membrane. Okay. So, now if you do an overall component balance for A, now let us do an overall component balance for A. So, that will give you the following relation: QF XF is equal to total mole that is going into the system per unit time. Okay. So, QF XF is equal to Q naught x naught plus QP YP. Okay. Total moles of A that is going into the system per unit time, total moles of system that is going out of the total moles of A that is going out of the system through the reject stream Q naught x naught, and that is going through the permeate. Okay. So, you can rearrange this equation, and this rearrangement will lead to give you XF is equal to Q naught x naught divided by QF plus QP divided by QF times YP. Okay. This is equation number 6. That means, you are dividing both sides by QF, and now you define the fraction theta. Theta is nothing but QP divided by QF, the fraction of feed that is going into the permeate. Now, if you divide define a theta, that is QP divided by QF. So, this becomes XF is equal to 1 minus theta times x naught plus theta times YP. Okay. This is equation number 7. Now, this equation can be reorganized to estimate the feed mole fraction, or that is there in the permeate. That means, you can find out the mole fraction of the feed from this. That means, a rearrangement of this equation can give you two things. Suppose x naught is equal to XF minus theta yp divided by 1 minus theta. That means, if you know the feed concentration mole fraction, if you know the cut, that means the how much per how much the fraction of the feed that is going into the permeate, if you know that means let us say 0.3 30% of that, and if you know the permeate concentration, and then x naught, that is the concentration of the mole fraction of the reject stream, can be calculated from this equation. Or if you know the other things, you can calculate the mole fraction of A in the permeate stream. That means, this or this xf minus x naught into 1 minus theta divided by theta. If you measure the permeate reject mole fraction, and if you know the what is the cut of feed fraction of the feed that is going into the permeate, and if you know the feed composition, you will be able to calculate what is the Yp, or the concentration mole fraction of A in the permeate stream. Okay. Qp is theta into Qf. So, you can get an idea, since Qp is theta times Qf, that is by definition the fraction theta, from the equation Qp Yp divided by Am is equal to Pa prime by T is equal into Ph x naught minus Pl Yp. This equation you have written earlier, that is the total flux of the of species A that is going into the permeate stream through the membrane. From this, one can calculate the value of membrane surface area. This will be theta times Qf times Yp multiplied divided by Pa prime divided by T is Ph x naught minus Pl Yp. Okay. So, from this equation, if you know all the other parameters, that means, if you know the sum of the parameters, or then you can calculate some of the other parameters, then whole right hand side will be known to you, then you will be able to calculate what is the membrane area that will be required for such a purpose. So, this is the design. So, if you know the feed conditions, if you know some of the other conditions, you will be able to calculate what is the permeate mole fraction and the amount of permeate that is going out of the system, that is a design parameter. Let us say you set it at 0.3 or 0.5 or 0.7, then you will be able to calculate the value of membrane area that is required. That means, if you set a cut of the permeate, that means what is the fraction of the feed that is going into permeate, you can have, and that means theta will be fixed, you are fixing the theta. Under that condition, you will be able to calculate what is the membrane area that is required for such a system, to design such a system. Now, what you can do, you can select several values of theta and calculate what is the value, what are the corresponding values of Am. That means, typically if you do that, then you can plot the value of the membrane area required versus theta. Okay. So, from that plot, one can get that if we have a if we fix up a fraction of the feed that is going into the permeate, then what is the corresponding value of the membrane area that is required for such a system. Now, if you closely look into the various equations, you can find out that let us do some design calculations. If you know, if you closely look at all the equations, you will be seeing that there are 7 variables in all. What are the 7 variables? They will be xf, the x naught, yp, theta, alpha star, pl by ph, am. xf is the mole fraction of the species A in the feed, x naught is the mole fraction of the species that is going in the reject stream, yp is the mole fraction of the species in the permeate stream, theta is the ratio of feed permeate divided by the feed flow rate, alpha star is the ratio of permeability of species A and B through the same membrane, PL by pH is the pressure ratio in the permeate side to the feed side, and AM is the surface area of the membrane. Now, generally 4 of them are independent. Generally out of 7, 4 out of 7 are independent. Now, we subdivide this problem and closely look into two cases. Case number 1 is that x f x naught alpha star P L by P H are given. So, these are basically operating conditions. Now, A alpha star is a property, that is the permeability of ratio of permeability of species A and species B. P L by P H at the operating condition, that is the pressure that you are maintaining in the permeate side and in the feed side. X f is the quality or the mole fraction of A in the feed, and the reject quality is set by you. So, let us say that this is the reject quality that we are going to have. Okay. Once you have that, then we are going to estimate what are the permeate quality y p and what is the theta, the mole fraction. If you set the x naught, the permeate the reject quality, then what will be the required value of theta that we are going to get. Okay. Theta and am need to be determined. Okay. So, we are going to get, you are having there are four parameters and 3 parameters you are going to estimate. Okay. So, that you can really design the whole system. So, first of all you are going looking into the equation 5.4, the equation 4 that we are going to have here, y p divided by 1 minus y p is equal to alpha star x naught minus P L by P H y p divided by 1 minus x naught minus P L by P H 1 minus y p. Okay. So, this equation can be written as that y p as a function of x naught alpha star and the ratio P L by P H. All these are known to you. Now, it is a quadratic equation. If you look into this equation, this if you multiply both sides, this becomes one term will be y p square and there will be another term that will be y p square. So, it is a quadratic in y p. That means, x naught will be known to you, alpha star will be known to you, P L by P H will be known to you, because they are given. Only one unknown is y p. So, you are going to get a quadratic in y p, going to solve that and you are going to get the value of y p. Estimate value of y p. I am not solving this equation, please solve this equation. There is nothing great in this equation, because all the other parameters are known. If you simplify this equation by cross multiplying it, it will be a quadratic in y p. Bring all the coefficients of y p square in one side and y p in one side and everything. So, it will be a quadratic equation. You know how to find out the roots of the quadratic equation and estimate the value of y p. Okay. Now, once you know the y p, you can get the value of x naught. Okay. X naught is given. So, you can get the value of theta. Theta can be calculated from equation 8. What is that equation 8? That is the x naught is equal to x f minus theta y p divided by 1 minus theta. Okay. This equation we have written. From this equation, y p is known, x f is known. So, you can y p you have estimated, x f is known. So, you can estimate the value of theta. Okay. So, it will be x naught minus x naught theta is equal to x f minus theta y p. So, it will be theta times y p minus x naught is equal to x f minus x naught. So, you can get the value of theta. Okay. Now, from equation 9, once you know the estimate the value of theta, you can calculate the value of A m as theta q f y p divided by P a prime by L P h x naught minus P L y p. So, you have already calculated the value of y p. You have already calculated the value of theta, P h x naught, and so x naught is known to you, y p is known to you, and PL, PH are all known to you. So, you know the denominator on the right hand side, and you know the first term on the denominator P A prime by L, that is also given to you. So, because membrane thickness is known to you and permeability value of A through the membrane will be known to you. So, you can estimate the value of AM or the membrane area required for this particular problem. Now, you can design the appropriate configuration to supply that much of membrane area, so that it can be the whole system can be designed appropriately. Okay. In next case that we will consider case number 2, and what will be that? In this case, xf is given, xf theta out of the 7 parameters, xf theta alpha star PL by PH are given. These 4 parameters are given and are going to estimate the permeate mole fraction in the reject stream and the surface area, that is membrane surface area, that is required to be estimated. Okay. Now, I am not going into detail. So, using these equation exactly like the case number 1, one can find out the value of Yp, the value of x naught and the value of Am, exactly like the previous, using the same set of equations. That means, using the same set of equations, one can solve this case as well. Okay. Now, there is something called minimum concentration of a reject stream . This concept is given when all the feed is permeated. That means, when you will be getting the, you will be extracting or recovering the feed, complete value of feed in the permeate. That means, in that case theta will be equal to 1, okay, QP is equal to QF. This case will be realized when theta is equal to 1. That means, QP will be is equal to QF. That is, you are extracting the full value of feed in the permeate stream, and the feed composition becomes xf is equal to Yp. That means, mole fraction of the feed will be equal to mole fraction of the particular species in the permeate. Now, for all values of theta less than 1, that is important. For all values of theta less than 1, Yp is greater than xf. Okay. So, anyway, so we substitute xf is equal to Yp in equation number 3, and you will be getting the minimum reject component XOM. In this case, this is minimum mole fraction of the reject component for a given xf, and this will be xf. If you substitute that value there, it will be xf is equal to 1 plus alpha star minus 1 PL over PH 1 minus xf, and this is alpha star 1 minus xf plus xf. So, that means a feed component. So, this is the value of minimum reject component for a given value of xf. One can plot XOM versus xf for different values of the feed composition. So, a feed component xf. So, what is the interpretation? The interpretation is this: a feed component having a composition having a mole fraction of xf, it cannot be stripped lower than xom, cannot be stripped lower than xom even with a very large membrane area in a completely mixed system. That means, the interpretation is, if you have a completely mixed system, even if you go for a very high membrane area, you cannot get a composition of the reject lower than this value. Okay. Suppose this value is 0.4 and you would like to go beyond this, what we are going to do? This is the maximum possible value, the lowermost, the minimum possible value that you can go for the reject stream composition, even if you supply an infinitely large membrane area. Now, if you would like to go even lower than that, what you have to do? You have to do the cascade system. What is the cascade system? You have to place such units one after another in series, that is in cascade. Okay. So, you go from xf, you go to xom in the first stage, and xom now will be now the feed composition for the next system. Okay. So, and you can calculate what is the value of xom in equipment number 2 or the unit number 2, you can calculate that, and like that you can go down below the minimum value of this if you have a several systems in cascade. Okay. So, next thing that we are going to do is the cross flow model for gas permeation. So, this is basically a more or less complete system whenever we are talking about a completely mixed up system. So, in this completely mixed up system, the models are pretty simplified, and this model will constitute by the overall material balance number 1, the balance equation for the solute A, the balance equation of solute B, and the permeation rate of solute A and the permeation rate of solute B, and the driving force in this case will be the partial pressure difference of component A and the partial pressure difference of component B. Now, using these 4-5 basic equations, one will be able to design the whole system for a completely mixed up system. Next, we go for the cross flow configuration, cross flow mode of permeation. Okay. So, in this system, let me draw a schematic first. So, this is the membrane, and your feed at high pressure with a composition, flow rate is Qf and Xf is the composition, the mole fraction of A in the feed, and there is it is a plug flow that occurs here. In the earlier case, it was a completely mixed flow, that means concentration is uniform everywhere in the permeate as well as in the feed stream, but in this case it will be a plug flow, and the pressure is pH at the higher side and this is the lower side is PL, and permeate you are going to collect as QP is nothing but theta times QF. Okay. And this is a low pressure side, and this is a high pressure side, and permeate is going to get like a cross flow 90 degree to the direction of the flow rate. So, you will be having now, if you have a differential area with a differential membrane area of dAm, and if the cross section, so this dAm is located between the length x and x plus dx. Okay. dm is the differential membrane element area that is located between the two locations x and x plus delta x, and the feed that is going here is q at the location x, and the other one that is going out is q minus dq at the location x minus dx. So, this is x minus dx. Okay. So, we are basically calibrating length from the other side, and the reject is going to get is at x naught q naught, and what is q naught? Q naught is nothing but 1 minus theta times q f. Okay, that is a schematic of a cross flow system. Longitudinal velocity in high pressure reject stream is quite high. Okay. The longitudinal velocity in high pressure reject side or reject stream is quite high. Since this velocity will be quite high, then we can assume a plug flow is prevailing there. Plug flow means there is no velocity variation. That means the velocity, this is a cross sectional area, and if the velocity profile is like this, then it's called a laminar flow. And for a turbulent flow, the velocity profile looks something like this, and for a plug flow, the velocity profile is flat. That means the whole thing moves like a solid plug or the solid velocity. So, it is basically the velocity is uniform, it is not varying with a cross section. So, if you remember, this is the laminar flow, this is the turbulent flow, this is the plug flow. From the laminar to the turbulent, if the velocity is very high, then this curvature is more or less lost, and it becomes almost flat, and as velocity increases, the curvature appears only at the wall. That is the turbulent flow. If you increase the velocity further, this curvature curvature of the velocity profile will be lost permanently, and you will be having a flat profile or the uniform flow profile. So, we call it a plug flow profile or uniform velocity profile, and it will be, we assume that it is basically prevailing in the reject side or in the feed side. Anyway, we will continue this discussion in the next class onwards, and we will be having the full we will write down all the equations regarding into this model, this cross flow model, and how to solve them. We also see that, and finally, we will be looking into the design of such system in the gas permeation or the gas separation case. Okay. Thank you very much.